So good afternoon to all you all. We had some technical issues right at the onset, so sorry for the delay. I shall wait for two more minutes and then I shall start. Right. Right. So today, and I shall answer your question later on. So don't worry about that. Right. All right. So today we are going to talk about convolution of continuous time signals, and this is one of the most important topics in this entire course. Right. This convolution is not just a mathematical construct. It actually represents how systems interact with signals, and other way around, how signals interact with systems. And not only that, for single input single output continuous time linear time invariant systems, we shall see that um, having this idea can give you much broader control over the system, as a matter of fact. So we shall learn about all those things, so in this course, in this particular topic today, right? So first of all, let's clear a few terms. Okay, in this course we shall be talking about single input single output single input single output linear time invariant system in continuous time, right? So those of you who are complaining that audio is not there, video is not there, please confirm, because in my feedback I am seeing everything is working, right? Yeah, audio was muted for a moment. Yeah, I have been having technical difficulties since the onset, so please let me know. Please confirm if the audio and video is fine. right? So let's start. So let's first clear up a few terminologies here. Okay, so I have mentioned this in your earlier classes. So there are a few terminologies regarding systems, and this is one of the primary topics where we shall actually learn about systems. And again, interaction of systems with signals and signals with systems. Right. Right. So with that said, say we have a system, right? We have a system, and that must satisfy a few criteria per se for this entire study that we are going to do today to be valid, right? So again, these are all simplifications, and simplifications are meant for keeping the things simple as needed, right? So the terminologies that we are going to use today are, you are familiar with these things, right? We are going to talk about single input, single output systems, right? So single input, so our systems need to be single input, single output for the most part for this to work. Again, what is single input, single output system? A system that has one single channel for an input and one single channel for an output. That's like that. So very simple to understand, right? Right. So, and the system should be linear and time invariant. Linear and time invariant. Right? So we discuss these terms in our regular classes, right? So the system must be linear, time invariant. Again, CISO is not entirely needed. Okay, the system does not need entirely need to be CISO. Okay, it is whatever we're going to study today is also applicable for MIMO systems, but this must be satisfied. So this criteria here, for example, is kind of an essential criteria. Okay, this must be satisfied for anything that we're going to talk about today to actually work, right? So with that out of that aside, let's start our discussion today, right? So again, we are going to talk about single input, single output, linear time invariant systems, right? The system has to be linear and system has to be time invariant. So those are the essential criteria here in this regard, right? So with that said, let's start with a very simple thing. For example, okay, say often what happens is we are given a system, right? I hope I could draw this well. Nope. Right. So imagine we are given a system, right? I'm saying this is an LTI system. So LTI stands for linear time invariant again, right? And I'm exciting the system with certain inputs. Say I'm calling the input to be xt, right? And of course the system will generate certain outputs. That's how systems are defined. Systems are things that have a physical or logical boundary or both, and they interact with qualifying signals, right? So imagine this input is a qualified input for this particular system, and this is the output, right? Now it's okay, or it's sufficient for us if we just physically have the system with us, right? If we just physically have the system with us, then it's just sufficient to have the system and deal with it like that, right? Without any particular issue whatsoever, right? So if we have a physical system, for example, an electrical circuit or a mechanical system or anything like that, we can excite the system with an input and we can observe the output, right? So that's quite understandable. There is no issue with that, right? But oftentimes what happens, we do not really physically have the system with us. Okay, often we don't have the system physically present with us, right? Right. Now in those scenarios, what can we do? We can model the system, of course, right? So for example, if you have an electrical circuit, okay, when you solve a circuit for your, maybe for your circuit theory classes and all, you didn't really have the circuit physically present with you, right? But you could still solve the circuit because you had a model for that, right? You know where the resistors went, where the capacitors, inductors went, where the transistors went, where everything went, right? You know exactly where everything went, and you could make a mathematical model per se for that particular system. Now imagine we are dealing with a system. Okay, imagine we are talking about a system where you do not really have a proper mathematical model to talk about, right? Right? So under those scenarios, what happens is we do not really have a direct way of modeling the system, right? So if you don't know what is inside the system, you cannot really model the system. You cannot really mathematically express what is there inside the system because you don't know what is there inside the system, right? Right? Or how the system really behaves. You don't really know. Under those scenarios, you cannot really make a mathematical model up for the system, right? But under those scenarios, if you know that the system is linear and time invariant, you can do something amazing with the system. Okay, so let me tell you that, and let me show you an example. And the example would be quite not an electrical example, right? It will be a day-to-day example, for example. Okay, so the idea is, if you have a linear time invariant system, then you can calculate something called an impulse response for the system. And what is the impulse response of a system? You just excite the system with an impulse, unit impulse, right? And I taught you about unit impulse. And what are unit impulse? Unit impulse signals. Unit impulse signals are very special signals, okay? And those can be considered to be the derivatives of unit step signals, okay? And we discussed about its many properties, right? But if we excite a system with an unit impulse signal, then the response we get is often called the impulse response. So this we have here, what we have here is known as an impulse response. Right? I'm going to tell you what I'm talking about here. But for the most part, try to understand that I can excite a system with an impulse input and I would get the so-called impulse response from the system, right? Now, the theory of linear time invariant systems, and we shall shortly learn that, tells us that if this is known to us, then we do not really need to have this system with us. Let me again repeat what I just said. I just said, if I have the impulse response of a certain linear time invariant system with us, then in order to find the output for any input to the system, we do not really need the system. Need to have the system. Try to understand. If we just have the impulse response with us, we do not need the system at all. Right? So that's quite weird. That might sound weird in the beginning, but with an example, I will make things clear. The idea is that for linear time invariant systems, if I have the system, it's good. If I don't have the system, but if I have complete knowledge of the impulse response of the system, then it is equivalent to having complete knowledge about the system. So that's how amazing things are really if the systems are linear time invariant. Okay, I will show you an example, don't worry. But if the impulse response is known to us, then we can actually use mathematics and calculate the response of the system to any input, right? So the mathematical expression tells you that if you know about the impulse response of the system, okay, if you know about the impulse response of the system, then if you excite the system with any arbitrary input xt, right, then you can calculate the response of the system. For example, the impulse response is ht and input is xt. Okay, for an LTI system, for a linear time invariant system, you can entirely calculate the output of the system to any arbitrary input. Again, this is an arbitrary input. This is an arbitrary input and this is an impulse input. Okay, then you can entirely calculate the output of the system to any arbitrary input by doing a mathematical operation known as the convolution. This mathematical operation is known as, we shall learn about that later on, right? So actually what we can do we can have the physical system, okay, and we can feed the physical system with any arbitrary input, and we can observe the output. Or if we don't have the physical system, we don't actually need the physical system as long as it is linear time invariant and I have complete knowledge of the impulse response. If so, then by having complete knowledge of the impulse response of the system, we can actually, without having the system present with us, we can absolutely perfectly calculate the response of the system to any arbitrary input by doing this mathematical operation known as convolution. Okay, and mathematically speaking, this actually gives you the output of the system. Okay, and mathematically speaking, this is expressed with this integral, and I shall teach you this in the next class, okay, where this formula actually comes from. But for the moment, just remember that this is the expression through which you calculate the convolution of two signals. But for the moment, try remembering this. And I shall explain everything, don't worry. Okay, I shall only explain the origin of this, or rather I can only explain the origin of this after you study Fourier transform. So yeah, things are quite intertwined in this case. So I shall talk about that later on. So don't worry about that. So this is the mathematical expression through which you can actually calculate the response of a system. So again, what I just told you, I told you that having complete knowledge of the impulse response of the system is equivalent to having the system physically present with us, right? So that's quite amazing, right, in reality. So with that said, let me show you a very rather say a very simple example in this case. Let me show you. Right. All right, so I think you can hear it, right? Please let me know if you can hear it, because I mean, having a feeling of this is very important. Having a feeling of this is very important, right? So this is someone playing a violin, right? Right? Yeah, I shall talk about the expressions, don't worry. Okay, but for the moment, please let me know if the audio is pretty clear, right? The audio is clear, right? So this is someone playing a violin, right? So this is someone playing a violin in a standard room, right? In a standard room, right? Okay, in a standard room. Now, you have, so for example, if you have an empty hallway, imagine if you have an empty hallway, okay, a big hallway or big auditorium, something like that, and it's empty, entirely empty, okay, then the sound, then the if you, for example, if you can play violin, then if you play the violin in an empty hallway, would it sound like this? Would it sound like this? Okay, this clearly actually sounds like a violin played in a normal room, right? Not in an empty hallway, right? Not in an empty hallway, right? Because you already might have heard how things sound in an empty hallway, right? If you play something in an empty hallway, things feel echoey, right? There will be lots of echo, okay, because it's an empty hallway after all, right? But this music here that you are listening here, for example, yeah, it's, yeah, so it is not played in an empty hallway, right? Now imagine I'm an amateur violinist and I want to have a feeling like how the violin playing sounds in an empty hallway, right? If I want to have a feeling like that, then I might have to book an empty hallway for me only, okay, and then I can play there and listen to the sound, right? But imagine that's not possible for me, okay, to book an empty hallway and play for myself, right? Maybe that's not possible for me. But I want to have a feeling how this sounds in an empty hallway. Okay, what can I do? Of course, my one easy option is to get an empty hallway and play it there, right? So that would be like having a physical system and applying the input to the system, right? So that would be like having a physical system and applying the input to the system itself, right? So that's understandable, pretty simple to understand, right? But imagine having the physical system for us is not possible. What can I do? I can then go back to the theory of linear time-invariant systems. I can go back to the theory of linear time-invariant systems, and I can recall that instead of having the system, so in this case, instead of having to rent an entire empty hallway, okay, maybe an entire auditorium, instead of having to book that, I can have the impulse response of the empty hallway with us. I can have the impulse response of the empty hallway with me, and I can use that to generate the output, namely as if I played the violin in an empty hallway, right? So how can I have a feeling, or how can I hear what my violin playing sounds like in an empty hallway? I have two options. One option is to book an empty hallway, go there, play for myself. So I'll be able to hear what my violin sounds like in an empty hallway. Or I can have the impulse response of the empty hallway with me, and then do a convolution operation with this sound, okay, and the impulse response of the empty hallway. And that, in theory of the convolution that I told you just moments ago, okay, in theory, it should provide me with an output that is representative of how this sounds like in an empty hallway. I think I got the idea clear, right? So with that said, let me ask you, my next question is, how do I get the impulse response of an empty hallway? How do I get the impulse response of an empty hallway? Any idea? How do I get the impulse response of an empty hallway? So I have to excite the empty hallway with an impulse input, right? So how do I get the impulse response of an empty hallway? What is the way of doing that? Okay. How do I get the impulse response of an empty hallway? Can anybody answer? Any random guess? So again, to give you a hint, what is an impulse input? An impulse input is a sharp, loud input, for example, in sound related terminology. Okay, an impulse input would be a very small width, okay, a signal or an input or a sound that lives for a very small amount of time, but it's pretty loud for that particular small amount of time. That would appear to be an impulse input for that particular system, right? As far as sounds are concerned, right? Audio is concerned. So for audio, an impulse input would be a very short-lived sound, but with a very loud bang, for example. No, not playing in the inside the water. So impulse, for example, what is impulse? Impulse is a very short-lived sound, but is a very loud sound because the amplitude is too high, right? The amplitude is too high. So it's a very short-lived sound, but the amplitude is too high. So what kind of sound is that? Can you give me an example of a very short-lived sound, but the amplitude or the loudness is too high? Yeah, actually we are trying to convert the impulse input to the violin's music, right? But impulse response to the violin's music. No, you're thinking too complicated. Okay, let me ask you a very simple question. Give me an example of a sound that's too short but too loud. Okay, I mean, give me an example of a sound that stays for a very small amount of time but has a large amplitude, large volume, right? Yeah, one of you are mostly correct. A bomb exploding, right? For example, okay, or cracker exploding, okay, right? Something like that. Yes, absolutely. So firing a gun would be the most precise example in this scenario, right? So if I ask you, what has a very, what are the sound that in particular has a very small time window, okay, happens for a very small amount of time, but has a large bang, for example, right? It will be like exploding a cracker or maybe firing a gun, for example, right? So again, let me go back. What do I want? Okay, no, dog whistle, for example, someone says dog whistle. No, it won't. I want a sound that's very small in time, right? That stays for a very small amount of time, but has a large bang, for example. I said bang, you try to understand what I said. Okay, for example, the amplitude rapidly rises up and rapidly drops down. So that would be like a gunshot or maybe a bomb exploding, right? So for example, again, what was my point? My point was to retrieve the impulse response of an empty hallway, right? So in order to get the impulse response of an empty hallway, what can I do? I can somehow get to the empty hallway and fire a bullet in there. Okay, make a gunshot in there. This might sound weird, but this is quite okay in some other countries, for example, not in India maybe. Right. So what I can do, I can go to the empty hallway and do this. See? So imagine I went to the empty hallway and recorded how a gunshot sounds like in the empty hallway. This is what a gunshot sounds like in the empty hallway. This is what a gunshot sounds like in the empty hallway. Okay, so this gunshot is representative of an impulse input, right? And this is what it sounds like in an empty hallway. See, you already have an echoing. Those who are using headphones, they might be able to hear this better, for example. Okay, so basically I'm firing a gun in an empty hallway, right? So that is what a gunshot in an empty hallway sounds like, right? So let me go back again. What was our question? Our question was that I'm a poor violinist, right? And I only get to play at my home, right? Right. So I cannot rent a empty hallway for me to play for myself. Okay. So, but I want to have a feeling of how it would sound in an empty hallway, for example, right? So instead of renting an empty hallway, I just went there somehow and shot a bullet, for example. And this is the gunshot. So now, for our mathematical purposes, for our subject's interests, this is my input. Okay, what is the input? The sound of the violin in a regular room. And this is the impulse response. And this is the impulse response of an empty hallway. Right? But my objective was to able to figure out what my music sounds like in an empty hallway. So what would I do? Instead of playing my violin in an empty hallway, I could take this audio. Where I'm playing the violin in a regular room, and this audio, which is the impulse response of an empty hallway, right? And do a convolution. So again, I just told you moments ago that when I do convolution like that, it immediately gives me the response of the system, okay, response of the LTI system as if we physically had the LTI system with us, right? So if I now convolve the gunshot sound, okay, the sound of the gunshot in the empty hallway, which is the impulse response of the empty hallway, with my violin that I played in a regular room, and if I do a convolution operation, in that case, I would get a sound that sounds like as if I played my violin in the empty hallway. So let me play that. Let me play it once again. I think you people got the point, right? So let me remind you again. We did not play the violin in empty hallway, okay, at all. But it still sounds. But it still sounds as if we played the violin in an empty hallway, right? How? Because for an LTI system, as long as the system we are talking about is representable in a linear time invariant fashion, the impulse response of the system is representative of the entire behavior of the system, right? That's quite amazing for any intents and purposes, for example, right? So as long as we have the impulse response of the system, we can have the entire behavior in our fingertips, for example, okay, entire behavior of the system, as long as the system is linear time invariant, right? So that's my entire point. And again, this is not at all played in an empty hallway. This is the mathematical convolution between the sound of the gunshot in the empty hallway, which is representative of the impulse response of the empty hallway, and again someone playing a violin in a room, and right, like that. So that's pretty understandable, I believe, right? Okay, so the important point to note here is that if I talked about an electrical circuit, okay, and gave you an example, it would not might have felt very intuitive for that case, because for an electrical circuit you are always, you people are all electrical engineers, you are always able to actually construct the circuit in a theoretical fashion and solve it theoretically, right? Solve it theoretically, or solve it like using PSpice or something like that, right? You can always do that. But for many physical systems, this kind of mathematical modeling is not always possible, right? Of course, for an empty hallway, there is an acoustic model. Okay, acoustic model means model related to sound, how sound echoes through and everything. Okay, but those things are taught to mechanical engineers, not you people, right? So hopefully you won't know how to do an acoustic modeling of an empty hallway. But if you could do that, you can get this without even calculating the impulse response ever. But my point is, many times, quite often, you would encounter systems for which you don't really know the internal composition of the system. You don't really know how the system is constructed internally, right? And often, even if you know how the system is constructed internally, often it's not a good idea to dig around and figure out how the things are constructed and then develop a mathematical model from inside out, right? That's often, then often what happens is the internal modeling, or modeling something from inside out, figuring out how things are constructed and then modeling the system, is often an infeasible idea, okay, right? So often what we look for is the impulse response of the system, and if the system is, okay, if the system is linear time invariant, or to some extent linear time invariant, okay, and we can figure out a situation where I can consider the system to be linear time invariant, then we can take the impulse response of the system and just be happy with it. Because as long as I have the impulse response of the system, the theory of theory of systems would tell me that as long as I have the impulse response, as long as I have the impulse response of a linear time invariant system, I have the entire behavior of the system at my fingertips. So that's how things really work in linear time invariant domain. So if you have any question up to this point, please let me know, because we are going to jump into mathematics, and we have a lot of demonstrations, and I also made some Python programs to show you, and this is again entirely done in Python. Okay, there's a famous electrical engineer named Alan Downey, and I will share you the links, so don't worry. There's a famous electrical engineer, Alan Downey, and he's a professor of signal processing, okay, at New York University, and he actually developed all these things. And my cats are interrupting things. Right. So with that said, let's deal with these things mathematically. Right. Yeah, of course. We the impulse response of the hall was recorded. Uh, yeah, impulse response of the sound that was recorded in the hall, that was the impulse response, right? So someone shot a gunshot in the, yeah, someone shot a, so this is the gunshot, for example. For example, that particular example, this is the gunshot. This is the gunshot. Okay. So someone shot a gun in the empty hallway. And this is what the gunshot sounded like. In the hallway. Okay, this is what the gunshot sounded like in the hallway, and this is the hallway, empty hallway. The system is the empty hallway. The impulse input is the gunshot, and the response, impulse response, was the gunshots, what the gunshot sounded like in the empty hallway, right? This is, this arbitrary input now is someone playing violin in a regular room. Okay, and the output, for example, would be someone playing violin in an empty hallway. Right? So someone shot a gun in the empty hallway. So that was the impulse input, and the sound that was recorded from the empty hallway of the gunshot, that was what the gunshot sounded like in the empty hallway. That was the impulse response. And we did a convolution operation with the input. What was the input? The input was someone playing a violin in a regular room, and the convolution operation gave me the output. And what was the output? As if someone playing the violin in the empty hallway. That is what happened, mathematically speaking, right? I think the idea is clear now, for example. Right. So please let me know if the idea is clear up to this point before we actually move forward. Right? Right. So let's try to understand. Again, someone asked, what is this, right? So this is tau, right? Tau is a special dummy variable, for example. You can write p, you can write x, you can write whatever, as long as it's a dummy variable, right? So, right. So this is how things, again, I shall tell you later on, I mean, on a future class, where this expression actually comes from. For the moment, try to understand that this is the expression for the convolution. Right. Okay, someone is asking, so why we needed the sound to happen in a small time? Because that is what impulses are, right? What is an impulse signal? An impulse signal has a very small time width, but it has a very large magnitude. Recall what an impulse signal is, what an impulse input is. An impulse has a very small time span. Okay, mathematically speaking, the impulse only happens to be at t equal to 0 and nowhere else. Okay, but it has a very large magnitude, right? Ideally an infinite magnitude, for example. So it's a very small, so it happens in a very small time window, okay, within a very small amount of time, because it's an impulse. Impulse happen in a very small amount of time, but has a very large magnitude. That is what impulses are, right? Again, if you have any question, please feel free to ask, because for this subject, having a feeling of the subject is more important than understanding the mathematics, in my opinion, again. Okay, because if you have a feeling for the subject, you can always go back and later on understand the mathematics of the subject. But if you don't have the have a feeling of the subject, if you don't have a feeling of the subject, you cannot always go back and understand the mathematics. Maybe if you do, you still won't have a feeling about the subject, right? And again, somebody is asking, how can we figure out a system is LTI or not? We have to separately check for linearity and time invariance. And linearity has two constraints. Okay, all of you know that linearity must support the scaling property and the homogeneity, the scaling property and the superposition property. So if a system satisfies the scaling property and the superposition property and the time invariance property, then the system is linear time invariant. Okay, so we actually discussed these things in a very early class when we had physical classes going on, right? So so we would be able to actually figure out whether a system is linear or how much linear, or, and so on, how much time invariance and so on, right? So with that said, let's proceed further and let's figure out a few important things, right? So let me go back, okay, and say, so let me ask you with simple examples, for example, right? Let me ask you with simple examples. Let me clear things up. Right. So again, we are dealing with the impulse response and the input, right? Again, but the thing is, even though I'm talking about the impulse response and the input, this convolution can happen between any two signals. Okay, this convolution can happen to any two signals. But for our intention purposes, we are talking about the impulse response of a system and the input. But this convolution operation is mathematically defined and it's applicable for any two signals. Okay, they do not have to satisfy any criteria at all. They do not need to come from linear time invariant systems. Okay, if we have two signals, we can always do the convolution. But what it means, that would differ for different situations. So with that aside, let's define right. Say this is the impulse response of the system, of a system we're dealing with, right? Say this is the impulse response of a system. So with this color, I'm drawing this is the impulse response of the system, right? So I'm just making up an arbitrary example. This is the input to the system. Imagine like that. Right. Right. So we have a drawing right now with us. Right. So so we are now trying to find out the convolution of these two signals. I think that won't be very difficult to understand. So this green one is an input to the system, and this purple one is the impulse response of a system. Right. We are trying to figure out the convolution of these two signals. Right. First of all, let's do this mathematically, and then we shall talk about this. Then we shall talk about this in a more what should I say, graphical fashion. Okay. But rather let's say start with the graphical fashion, for example. So let's go back with the expression for the convolution. Okay. Try to understand what I'm talking about here. Okay. So what is the variable in this convolution operation? The variable in this convolution operation, for example, as long as we're talking about here, is the tau, for example. T is a constant, try to understand. Here T is a constant. Okay. I believe you understand that T is a constant, right? That's quite understandable, right? T is a constant. Now, since T is a constant here, so for different values of T, I would have different expressions for here. For example, I would have different expressions here. So, and the area would be, the integration would be basically the area under the product of these two graphs. So again, try to follow carefully, for example. So again, look at this one. We are trying to look at this one. Okay. So in this regard, this green one, for example. Okay. Right. So let's try to calculate what happens when when t is equal to 0. Say when t is equal to 0. So what happens when t is equal to 0? So we are calculating the output at t equal to 0, like that, like that. And this expression, the convolution expression, okay, here if I put t equal to 0, what expression do I have mathematically? The output of the system can be calculated with this integration. Right? Right? And now here t is equal to 0. So you basically have minus tau. So try to understand, we are doing this integration, right? We are doing this integration. So now, instead of writing t here, okay, so instead of writing t here, so instead of writing t here, if I write tau, okay, so if I write tau, then what do I have? So now, try to understand what happens. I want to calculate this. So this signal does not have any issue. So this is ht, like this was ht, now this is h tau, right? Now what are we calculating? We are calculating x of minus tau. So this is x tau now, right? So instead of being t, this is x tau. Now how do I get x of minus tau? How do I get x of minus tau? Question is, how do I get x of minus tau? I get x of minus tau by just doing a time flipping here, right? So this is x tau. If this is x tau, how do I get x of minus tau? So this is x tau. How do I get x of minus tau? By doing a time flip here like that, right? So let's do that. And if I do a time flipping on this, this is what I'm going to see. So this is now, instead of being x tau, this is now x of minus tau. Yeah, I just flipped with respect to vertical axis, right? Right. Now, in order to calculate the output, what do I have to do? I have to multiply these two signals. So I have to multiply this signal represented in green with this signal represented in purple. Multiply this signal and calculate the total area under the curve between these two signals. Okay. Question is, can I do that? Of course I can do that. If I multiply these two areas, okay, try to understand. Wherever this signal is 0, the green one is 0, okay, wherever the green signal is there, actually not 0, okay, wherever the, again, just to give you the values, so this is 2, this is 1, huh? Okay, wherever the green signal is, again let me erase those, wherever the green signal is not 0, okay, this purple one is 0, and wherever the purple signal is non-zero, okay, has a value, this green signal is 0. So if I just multiply these two signals, for example, here, okay, their product is going to be 0 for this particular example, okay, right? There is no common area they share, and since they don't share any common area, so their product's area is also 0, and so eventually this integral is 0. So let me know if you understood what I just said. So this integral is 0. No question about that, right? Right, I believe you got that, right? So similarly, if I say t equal to minus 1, instead of 0, say t equal to minus 1. So we are calculating the output when t is equal to minus 1. And how do I do that? Again, do the same integration. Now again, try to understand. Okay, I'm explaining a different, okay, let me explain once more. Okay, so okay, some of you saying, okay, you do not understand, right? So How do I calculate the convolution? I do calculate the convolution with this integral by evaluating this integral, right? By evaluating this integral. Now look carefully at the integration. What is the variable for integration in this? The variable for integration in this is tau, right? Not t, but tau. But what is the variable for the output? That's t, right? That's t, right? What is the variable for the output? That's t. So basically, we are calculating the output of the system at different points here, right? So when t is equal to 0, say I want to calculate the output of the system when t is equal to 0, right? So I would put t equal to 0 here and then calculate this integration, right? I think that's clear, right? If I want to calculate the output at t equal to 0, I have to put t equal to 0 here and then calculate the integration. Because as far as the integration is concerned, t is a constant and tau is the variable for integration, right? So when I want to calculate the output of the system for t equal to 0, okay, I have to put t equal to 0 here. That would represent a constant inside the integration, okay? And we have to integrate accordingly, right? Up to that point, I think it's clear, right? So we did that. Let's write it mathematically. I want to calculate the output of the system when t is equal to 0. So I want to calculate y0. Instead of just saying yt, I have to calculate y0. Okay. And if I put t equal to 0 in this expression, I would have h tau into x of 0 minus tau. So that's h tau into x minus tau d tau. That integration from minus infinity to plus infinity. Right. So I think that's clear, right? So I think that's clear, right? So we're actually calculating this integration. Oh, okay, forget this. Huh? Let's forget that. Right. So we are actually calculating this integration. I think this is fine, right? So now we are trying to mathematically figure out what we have as h tau. Again, tau is just a dummy variable, right? It's a dummy variable. So we can write p here, q here, whatever we want here. No, it won't matter, right? It's a dummy variable. Okay, it is just there for the name. It's a placeholder name, right? I can write whatever I want. So it doesn't matter. So h tau would look exactly the same as ht. Okay. Now what is ht? Ht is this one, right? So this was ht. So this would be h tau. Instead of saying t, if I say tau here in this axis, okay, this would be this signal, this purple one, that would represent h tau, just like ht. It's a very simple thing to understand, right? Okay. And what about x tau? X tau here, right? That's our x tau, because that was our xt. So this would be our x tau. So there is no difference between xt and x tau, again, once more, right? Right? Now we are trying to multiply two signals, but not these two. We are trying to multiply two signals, but not these two. We are trying to multiply two signals. What two signals? Which two signals? We want to multiply h tau with x of minus tau. Okay. We want to multiply h tau with x of minus tau. Okay. So this is x of tau. This green one is x of tau. Okay. So I want to first get x of minus tau. So how do I get x of minus tau? I take this x tau and flip it about the vertical axis. So it's a time flip. Okay, we talked about this in earlier classes. So it's a time flip. So I take x tau and flip it vertically. So if I flip it vertically, so instead of jumping here and going up to this point and staying up and ending at t equal to 1.5, it will jump here and go back and like that and end at t equal to minus 1.5 and so on. So I do a vertical flip for this, because I don't want to multiply h tau with x tau. I want to multiply h tau with x of minus tau, right? So how do I obtain x of minus tau? I just take this signal and flip it vertically, a vertical flip like that. right? But for conveniently for me, I can do a vertical flip very easily. So I think you got up to that point. Please let me know if you did not get up to this point. So if I do a vertical flip, okay, I'm doing a shifting right in front of your eyes, but that is representative of a vertical flip. For example, if I take this signal and do a vertical flip here, okay, so yes, this would be mirror image to this. So the result would somewhat look like this. So that's not a problem to understand, I think. So that is representative of a vertical flip here, for example. Even though I shifted, don't mind that. Okay, don't mind that. Try to feel that this is the vertical flip. So now instead of being x tau, this is x of minus tau. So please let me know if that this is clear up to this point. Right. So we have h tau. So this is h tau, this purple one, and this green one is x of minus tau, and we want to multiply these two. So multiplying two signals might seem difficult at first, but what am I doing? I'm just multiplying their values, right? Multiplying their amplitudes, values, whatever you want to call them. Now look at these points. Look at these points. So for example, look at t equal to minus 2 at this point. Look at this point. Look at this point. Okay, at this point both of the signals are 0. So their product is also 0. Right? No problem. No question asked, right? That's understood. Look at this point. Again, at this point, at t equal to minus 1, this signal, okay, x of minus tau, has a value of 1, so has a value of 2. But this purple one, which is h tau, has a value of 0. So their product is again 0. At t equal to 0, at this point, at this particular point, at t equal to 0, okay, this green signal is transiting from a value of 2 to a value of 0, and this purple signal is transiting from a value of 0 to a value of 1, right? So basically at this point both of them are 0. Okay, both of them are 0. Okay, because this transited from a high value to a low value and ended at 0, and this transited from a low value to a high value and started from 0. So both of them are 0 again, right? And again afterwards, after t equal to 0, say for example at t equal to 1.5, somewhere in the middle here, for example, so t equal to 0.5, say, okay, try to understand, tau equal to 0.5, for example, at this point, okay, the green one is 0 and the purple one is 1. So multiply them, you get a 0. Again at t equal to 1, sorry, at tau equal to 1, okay, at tau equal to 1, this green one is 0, this purple one is 1 again, or transiting from 1 to 0 again. Okay, whatever it is, the product is 0, and so on. The product is, for the rest of the time, is 0. So this entire product of these two signals, so if you multiply these two signals for the entirety of the tau span, not the time span but the tau span, for entirety of this dummy variable span, the product is 0, the multiplication is 0. Okay, so the area under the curve is also 0, and this area under the curve is representative of the output of the system by means of the convolution theorem. For example, by means of the convolution property, is representative of the output of the system, okay, at t equal to 0. So by convolving these two signals, by convolving I mean by doing a flip here and shift, for example, and calculating the overlapping area and evaluating the overlapping area like that, okay, and that calculating that overlapping area gives me the output of the system, okay, this overlapping area. Okay, things will be much clearer with slightly more concise examples, but I think this is fine up to this point. Please let me know if you still have queries. So there is no common area. So if I do the product multiplication, yeah, they end up being 0, right? So please let me know if you understood this. So in a similar fashion, I hope you got this. Again, please ask if you did not get this. So if t equal to minus 0.5, say t equal to minus 0.5, so I'm calculating the output at minus 0.5 like that. So what do I get? So from minus infinity to infinity, hold on, huh? My cats are pulling off a rampage here. Yes, we're actually going to deal with that. I mean, what if they share a common area? Of course, we are going to talk about that. Right. So with that said, so for example, I want to calculate the output when t is equal to minus 0.5. So let's go back to the formula expression for the convolution, right? So here I am putting t is equal to minus 0.5, right? So let's do that. So I'm writing the expression. So that would be h tau x of minus 0.5 minus tau d tau, right? I want to integrate that. But again, try to understand, what did I already have? I had x of minus tau. Now I want to calculate x of minus half minus tau, right? X of minus half minus tau. Please do tell me someone, what do I need to do to x of minus tau in order to get x of minus half minus tau? What else do I need to do? And again, we talked about the shifting properties and everything in an earlier class. Please someone let me know. So we already have x of minus tau. We already have taken care of the minus sign with tau. So I have to do a shift. Would it be a left shift or right shift? I want to represent x of minus 0.5 minus tau. So I need to take the green signal, and what do I need to do to this? Do I need to do a left shift or a right shift, and how much amount? Please someone tell me, then I will do it. Do I need to do a left shift or do I need to do a right shift? Or if so, how much? Someone says shift right. Okay. Do I need to do a shift right? So you are confused between shift left and shift right, right? So let me say here. Oh, I already flipped the vertical axis. The vertical axis flipping has already been done. So this is x of minus tau already. Okay. X of minus tau already. So let me say. So I want to calculate x of minus 0.5 minus tau. And how do I get that? I get that with this minus sign common and plus 0.5. So that represents a vertical flip. We already did that. That is what the vertical flip gave me. Okay. We already did a vertical flip. Okay. And then we have a plus sign. What does it represent? Is it a left shift or a right shift? Is it a left shift or a right shift? I want to hear from you. We did already flip the vertical thing, and this plus 0.5 represents a left shift, right? This 0.5 represents a left shift, right? Yeah. So vertical flip done, and I want to do a left shift of half unit, right? So I think I got that out. right? So now I want to do a left shift by half unit in time, right? Right? So now instead of having x of minus tau, I now have x of minus 0.5 minus tau, right? And in order to calculate the area output of the system, what do I need to do? I need to figure out the overlapping area, common area. Okay, multiply them, calculate the overlapping area, and basically take the entire area. That will be the output, because that's the integration, right? So what is the overlapping area here? What is the common area? Area of the product. What is the area of the product here? Question is, do they share any common area? Do they share any common area? Someone please let me know if they share any common area. Yeah. So all of you agree that they don't share any common area. Of course, when they were almost overlapping, they did not share any common area. Now they don't at all. Okay, right? So all of you agree that they don't share. This does not share any common area. So the output of the system is again 0. Right? Right. So question: what if I want to calculate the output of the system at say at t equal to 0.5? Let me say t equal to 0.5. Yeah, that would be nice. So t equal to plus 0.5. So I am calculating y 0.5, and that's integration from minus infinity to infinity h tau x 0.5 minus tau. I think you got the expression already, right? So I now want to calculate this area. So x of 0.5 minus tau, right? So I want to calculate this again, x of 0.5 minus tau, and find the overlap of the product, and then calculate the area accordingly. So, all right. So this is x of minus 0.5. So this was x of minus tau. Question is, what do I need to do to this signal in order to get x of plus 0.5 minus tau, x 0.5 minus tau, right? What do you need to do to this? Again, I want to have x of 0.5 minus tau. So that's x of minus tau minus 0.5. That's a vertical flip, and that represents a right shift by 0.5 seconds, right? So with that said, I already have vertically flipped the signal, and I need to do a right shift by half second, right? So now I'm doing a right shift by half second. Right. So that's my x of 0.5 minus tau. Right. Question is, yeah, when you say flip with respect to t, you did mean vertical flip. That's right. Or time flipping, right? So no issues with that. So question is, to tell me what is the overlap here. So if I take the product, multiply these two signals, try to understand, when I multiply these two signals, okay, this portion is 0, right? This portion is 0. If I multiply these two signals, this portion is also 0. Only this portion where they overlap exists, right? And what is the product of these two signals? The product is kind of represented with this. Okay, let me open another layer. the product is represented with this entire area. Right? This entire area is representative of the product, because within these 2 points, so within these 2 points, so this is again 0. Okay. Within these 2 points, which is 0.5 here, within these 2 points, try to understand that this signal has a value of 2 and this signal has a value of 1, so their product is 2, of course. So this is the overlapping area, this is the product area, right? So this area is going to give you the value of the output of the system. But please let me know if you understood the idea behind this. So again, if you're talking about these portions, one of them is 0, one of them is something, right? Product is 0. If you're talking about these portions beyond 0.5, okay, one of them is 0, one of them is something, again the product is 0. But between 0 and 0.5 tau, okay, both of them have some values. This one has a value of 2, this one has a value of 1. So this is the multiplied area. So what is the multiplied height, for example? These are the height of 2, these are the height of 1. What is the multiplied height? Multiplied height is 1 into 2, so that's 2. And what is the span, time span? Of course 0.5. So what is the area? What is the area in this regard? What is the area? So height into width. And what is the area? So of course you are actually doing, I am doing height into width because these are rectangles, right? But otherwise I would have to do integration, right? But if this area is, for example, 2 into 0.5, so that's 1. That's 1, right? Right, that's understood, I think, right? The only problem with this handout that I'm going to give you later on after the class is that the handout won't be representative of the entire thing, because I'm modifying the handout as I'm doing it. Right. So yeah. So this video will be representative of what we have taught, what we have studied today. Anyway, so that's understood, right? So if that is understood, then please let me know if you understood this, because I'm going to delete this shortly. Okay, I believe all of you got this. Let me get rid of this. And here the area is 1, so the output is 1. And again, just try to recall, try to understand that right off the bat, we did not know anything about the system. We only knew about the impulse response of the system. We did not know how the system has an input-output relationship. We did not have any mathematical expression for the behavior of the system. We only had the impulse response of the system. And on the basis of that, we are calculating the output. Okay, that is the important point to note here. Okay, we did not know anything else about the system. We only knew the impulse response. And again, knowing the impulse response of the system is just sufficient without any issue, right? Right. So now we are calculating the output of the system when t is equal to 1. So we are calculating this. So output of the system when t is equal to 1. Again, from the convolution property. So now let's go back again. This was our formula. Again, in this integration, tau is the variable, t is a constant. Okay. So now we are putting t equal to 1. So we are calculating the output of the system when t is equal to 1, right? So if I do that, put t equal to 1, I have this 1 minus tau d tau, right? We are calculating this area. And again, we are calculating x1 minus tau. And I believe all of you would agree to me that this would, okay, what happened? Am I only at 3? No. Okay. all of you would agree that this is just this. So this is x of minus tau, and if I right shift it by 1 unit, I get x of 1 minus tau, right? So that's my x of 1 minus tau. Again, do tell me if you have any query. And now we are trying to calculate the overlapping area. Right? Again, overlap of the product here in this guy. So again, when t is beyond 0 in the left, okay, when t is before t equal to 0, when tau is before 0, for example, the product is again 0 here. Okay, again after t equal to 1, the product is once again 0. But between 0 and 1, the product is not 0. Okay, and this is the representative of the product area. Multiply these two signals, and when you multiply these two signals, this has the value of 1 and this has the value of 2. So that will be the product, right? Please let me know if you understood this. Yes, absolutely. The area is 2. So this is the area. So area will be 2, right? Again, area of the product. Okay, we are simply calculating the area like that just because we have like rectangles, right? If we had anything else, we would have to multiply the signals like in the way you do it in mathematics and then integrate everything, right? So I'm showing you with a very simple example just because, so that's so that you have the idea, then you can work out problems, right? And doing an integration for a computer is not a very difficult task. Okay. Anyway, in any case, that's very simple to understand, right? So the area is 2. Of course, understandably, the area is 2. So again, let me go back, and the output of the system. Okay, did I write it on layer 3? My God. Hold on. Right. So the answer would be 2. Yeah. Right. So now let's calculate the output of the system when t is equal to 1.5. Let me see if that's anything of interest. Yeah, when t is equal to 1.5, say. Okay. So y 1.5, we are calculating y 1.5, and that will be this integration from minus infinity to infinity h tau x of 1.5 minus tau d tau, right? So I am calculating x of right there like that. So let me just okay, I'm making the same mistake again. Hold on. Okay, this is the problem you encounter when you are teaching online for the first time ever in your life. Right. No issues, right? So we're calculating x of 1 minus x of x 1.5 minus tau. So that will be a little more right shift like that. So that's gonna be x of 1.5 minus tau, right? And again, beyond t equal to 1, beyond tau equal to 1, the overlapping area is 0, the product area is 0. Again, before tau equal to 0, the product area is again 0. But between these 2 points, the product area does exist. Okay, yeah, and product area does exist, and the area kind of looks like this. Okay. So again, understandably, the area is again 2, right? So again, the output at that particular point at t equal to 1.5 is once again 2, right? So at this point, the output is equal to 2, right? So we're calculating the output at t equal to 2. So we are calculating this. So integration from minus infinity to infinity, h tau x of 2 minus tau d tau. So we are calculating that. So let's go back. So we are calculating the output at t equal to 2. So when we are doing that, again we have to shift this signal. Okay, let's do that again. Right. So if anyone has any question about the shifting or anything, please feel free to ask. That's 2 minus tau, right? Right. So understandably, the overlapping area has now reduced, right? The overlapping area has now reduced, and this is overlapping product, I mean, and this is the overlapping product, right? Yeah. So the height is now, so this is this is 0.5, right? Okay. The height is now 2. The area, so this is basically 0.5. So this area is 1. So the output at t equal to 2 is 1. Okay? That's equal to 1. And let's calculate output at t equal to 2.5. That's y equal to y 2.5. That's equal to this integration. Right? So we have x 2.5 minus tau. Again, if you are happy with this, let me delete this then. Hold on. Right. So here we have x 2.5 minus tau, and of course once more we don't have any overlapping area, right? Right. So when you are able to figure these things out, so it makes me happy, feeling that you actually understood the problem. That's 0. What is the output at t equal to 3? What is the output at t equal to 3? Of course, that will be even simpler in this case here, for example. What did I just do? So at t equal to 3, that will be the scenario. Like that. Okay. So for there is no overlapping area, the answer is once again 0. So let me go back and put a generic case in this. Okay, let me go back and put a generic case so that actually those who are actually following this handouts, they would have some point to refer to. Something to refer to, right? So this is an arbitrary position where this is t and this is x t minus tau. Okay, and this is the overlapping area. Again, this is just for the sake of the handout. Okay, you might have already understood when t is 0.5, it's like that, and so on. Right. You got the point. Right. So that's how we actually, in spite of knowing nothing about the system other than the impulse response of the system, we were able to calculate the output of the system to some arbitrary input here. Right. So with that said, we will actually end our discussion with a few examples, with few demonstrations per se. Okay, but if you have any question, feel free to ask me now. Okay, there are a few simplifications to this expression. Okay. And before we can actually talk about the simplifications that we can have, let's talk about something called causality. Okay, in fact, let's not talk about causality because we did talk about causality in our classes, in our physical classes. Okay, so for causal LTI systems, instead of saying that, let's say we're talking about causal signals. We talked about causal systems. Okay, causal systems are, let me again explain the term. For a causal system, the output at any given instance can be determined entirely based on the knowledge of the present and or past inputs. No knowledge of future inputs are required. In that case, the system is called a causal system, right? Someone says, what will happen if we impose a signal with any constant? Okay, yeah, we shall see a few examples, don't worry. We shall demonstrate a few examples because doing these things like with a tablet and everything is a very difficult task actually, really. Okay, so we have some Python examples we shall see, okay, with proper animated examples, so you shall get to have a better experience than this. Right. So with that said, let's talk about causal signals. So definition is this. Okay, xt is considered a causal signal if and only if. So in mathematics, if we say if and only if, the criteria is both necessary and sufficient. Okay, if and only if x t equal to 0 for all t less than 0. So if you got it, let me know. So then the signal is considered causal. Okay, so a causal signal, let me write it here. So a causal signal has a 0 value whenever time is less than 0. Okay, so whenever time is less than 0, causal signal must always have 0 value. Okay, if that is so for a signal, then the signal is considered causal. from that one can actually prove, which I'm skipping in this regard, but which we could prove, is that I think you got the idea of a causal signal, right? As long as t is lesser than 0, okay, the value of the signal is going to be 0. If that is so, then the signal is considered causal. And one important corollary that we can actually prove pretty easily is that the impulse response of a causal system, okay, the impulse response of a causal system is always a causal signal. Again, recall how we defined causality of systems. Okay, in terms of systems, we define causality in this way, that the present output of the system can be determined entirely based on the knowledge of the present and past inputs. Okay, that in turn results into this, that the impulse response of a causal system is a causal signal, is always going to be a causal signal. Okay, yes, for example, unit step is definitely causal, right? Ut is causal. Okay, for example, delta t is also causal. Okay, rt is causal. Okay, as long as if you have t less than 0, if the signal is always 0 when t is less than 0, the signal is causal. And the impulse response of a causal system is going to be a causal signal. So they are all quite intertwined in this regard, right? So in this regard, now we have this general expression for the convolution, right? We have this general expression for the convolution. So the output of a system is determined, for an LTI system, is determined by this convolution operation, xt into ht into xt. Okay, and that was this integration from minus infinity to infinity, and we had h tau x of t minus tau d tau. Now let's do a simple variable substitution. Let us say, let's say t minus tau is equal to p. I'm doing a variable substitution, right? Okay, right? I don't think there is any issue with this. So d tau, so minus d tau would be dp, and that would be d tau is equal to minus dp. I'm doing a variable substitution in the formula for convolution because I want to prove a very important point here, which you need to understand very clearly. Okay, and of course we are doing this, so let's go back to our school levels. Okay, so we have tau here, we have p here, and we are doing the value substitution, for example. So tau varies from minus infinity to plus infinity. When tau is minus infinity, t is any finite value. So when tau is minus infinity, p is plus infinity, and when tau is plus infinity, p is minus infinity, right? Right? So we are now doing this substitution. Again, we are just substituting for the dummy variable, right? So with that said, so we have the output of the system, which is again the convolution of ht with xt. That was integration from minus infinity to infinity. Now we are substituting tau with p, so we would have from infinity to minus infinity. Okay, now instead of h tau, look carefully, instead of h tau, okay, we also have something called tau equal to t minus p. Look carefully. So instead of h tau, I have h t minus p. Doing simple substitution, right? H t minus p, and instead of t minus tau, I have p. So I have xp, and I have minus dp, of course, because of this d tau is minus dp. So I put a minus sign here and I've written a dp here. I don't think there is an issue with this. And this can be written as, of course, this minus sign can be taken care of by just reversing the limits. So I now taken care of the minus sign by reversing the limits. So I have h t minus p and xp dp, and again try to understand that p, tau, all these things are nothing but dummy variables, right? Okay, you can might as well put some cow, donkey, or whatever you want here, right? So these are just dummy variables, right? You can write whatever you want here. So I can also happily put my name here. Okay, I can say something like that. It won't harm anybody, right? That's the name of the variable. So instead of saying that, I can also say that. I'm just changing the name, okay? Because these are just dummy variables. Okay, notice that p, tau, these are just dummy variables. Okay, so I can write that. But what is this expression? If I just rearrange things, look carefully, what does this one look like? If I just rearrange things, this is what it looks like. But what is this? This is xt convolved with ht. There's a very important distinction. Try to understand that we started with this convolution, ht convolved with xt, and we saw that this is equal to xt convolved with ht, right? Right? You got the idea, right? So what am I trying to say? I'm trying to say that the convolution operation is commutative in nature. So what I just proved is that the convolution operation, which gives me the output of the system when the impulse response of the system is known, the convolution operation represented with this star, okay, is commutative in nature. So which means this is perfectly valid. Okay, and so is this. If I consider this to be my property, this to my expression h, this is going to be from minus infinity to infinity h tau x of t minus tau d tau, and if I consider this to be the property, then xt convolved with ht gives me this integration. Right? So these two are identical in nature. So what I'm saying is that convolution is commutative. But that's the mathematical way of saying things. What is the engineering way of saying this? That convolution is commutative. Okay, the idea that convolution is commutative, this is mathematical, right? But what is the physical significance of that? This is the physical significance. Say this is the physical significance. Okay, say we have a system, again LTI system. Okay, so this is LTI system number 1, right? This has an impulse response. This has an impulse response. So when I excite this, let me just bring this here, right? And there is another LTI system. I'm calling that LTI system 2. Right. So when I excite the LTI system 1 with an impulse, okay, I get the impulse response of the LTI system 1. Imagine the impulse response is ht, right? And then if I excite this LTI system 1 with any arbitrary input xt, I would get an output of yt. And how do I calculate yt? Yt is simply going to be the convolution of ht into xt, right? Now imagine, so this is the impulse response of system 1. Imagine I have another system 2, such that when I excite this particular system, I instead get this as the impulse response, right? So try to understand. Imagine this signal that I used as the input to system 1 appeared as the impulse response of some other system, right? Appeared as the input of some other system. Okay. So this is a system which, when excited with an impulse input, generated this signal. Okay. Then if I excite the same system with the impulse response of the first system, I get the same output. Just because the convolution property is commutative in nature. Right? So the impulse response of this system was xt, and the input to this system was ht. So the output was xt convolved with ht, and the impulse response of this system was ht, and the input was xt. So output was ht convolved with xt, and since xt convolved with ht is identical to ht convolved with xt, the output of these systems are identical in nature. So in this understanding, we can very easily say that LTI systems and their responses are interchangeable in nature. Okay, LTI systems and their responses are interchangeable in nature, and we actually established that idea with that example. I could have an empty hallway and play my music there to hear how it sounds like in an empty hallway. Or we could have the impulse response of the system because it is entirely representative of the system. So with that analysis, or with that understanding, we can say the impulse response of a system is impulse response of an LTI system is identical to the system itself. The entire behavior is encapsulated with the behavior of the system, right? So if I have the impulse response of a system, the entire nature, entire behavior, what it can do, what it cannot do, is entirely contained within the system, right? Within the behavior, within the impulse response of the system. So with that said, if you have any confusion so far, let's start, right? Let's write a simple simplification, right? So if you have any confusion, please let me know. So please, my request is, please don't spam the live chat. If you have any question, please ask. All right. So by that simplification, we already know that let's go back. We already established that causal signals are those signals for which the value of the signal is 0 when time is less than 0, and the impulse response of a causal system is always a causal signal, right? So with that said, okay, the expression for convolution, which is yt is equal to this, d tau. Try to understand when tau is less than 0, then this signal is 0 for a causal system. Now for a causal system, excited with a causal signal, okay, so causal system, so the impulse response is causal. So this signal has a 0 value before t is equal to 0, right? So this will have to be reduced to 0, because before tau is equal to 0, this value will be 0. So there is no point of integrating, right? And also, since the signal we are talking about, the input we are talking about, okay, the excited with a causal signal, this is also causal, okay, this is also causal, then this internal argument value must also be greater than 0. So I am saying t minus tau must be greater than 0, right? Must be greater than equal to 0. Because if t minus tau is less than 0, then again this signal will be 0, because again the system is being excited with a causal signal. So my criteria is that tau less than equal to t. So going with the integration up to infinity is again absurd here or useless here. We can simply truncate the integration to t, because tau should be less than t, because if tau is greater than t, this becomes negative, and since x is also a causal signal, that becomes 0. So this is the simplification we can obtain if a causal system is excited with a causal signal. So that's a simplification, right? That's a simplification, right? And also this is because of the commutative property of convolution. We can say that this is x tau into h t minus tau d tau. That's for causal system. Okay, that's a special note. Keep that in mind, right? So whenever we are dealing with causal systems and causal signals, so we have this idea, or this simplification rather. Instead of doing the integration from minus infinity to plus infinity, we can simplify the integration like as such. Right. So with that said, that is the end of discussion as far as this goes. Okay, let me save this, huh? Because things are going wrong from the very beginning today. Okay, so let me start with Jupyter Notebook server, and let me show you a demo, a few demos rather. I'll send you the files anyway. So right. So let's start with the example we actually discussed today. A similar example, slightly more difficult to understand, but similar example. Right. So we're checking the convolution, right? Right. So again, in this example, okay, this black one, okay, this black one is the input to the system. Okay, this red one is the impulse response. So we can either flip the input or flip the impulse response, okay, and shift it. So this red one is ht minus tau, right? And I am varying t and finding out the overlapping area and calculating the integral, right? So see, this value here is representative of the integral, right? Integral of the product, right? When t is equal to -1, there is no overlap for this example here. Okay, again I flipped the red one, right? Because that has to be flipped. One of the signals must be flipped and shifted, right? That is how convolution works, right? So say up to zero, there is no overlap. Since there is no overlap, the output of the system is 0, right? This is representative of the area or the output, which is the convolution here. I think you got it, right? So let's increase the value, right? So now we have an overlapping area. The moment we have an overlapping area, so this is representative of the overlapping area, and that's the output. Increase that. Okay. We have increased the overlapping area. The output is also increasing because the area is increasing. That's too much. That's too much. Right? We got that, right? Right. So let's increase it further. Let's make it 2. So we have the output at maximum possible value, because of course from the figure you can figure out that this is the maximum possible overlap these two signals can have, right? Now let's increase beyond that. Of course, the moment we increase beyond that, this is the maximum overlapping area. Okay, so now the output is reducing, right? And if I go further, the output is again reducing. If I go even further, the output is again reducing, right? Now if I go even further, the output is also reducing. Okay, again reducing, and see, that is how now the output has now become 0. That is how the entire overlap did work, right? So that is how this particular, again I shall give you the files which you can execute in Google Colab, right? Now let's see a simple example, one more example. Let's start with 0, 0, 0. All right. Right. So this is a square pulse. And this is the flipped version. The red one is the flipped version of the impulse response of a series RC circuit. This is the impulse response of a series RC circuit. One is the flipped version. This is H minus tau, not H tau, but H minus tau. We have just flipped. Okay. So this is the impulse response of a series RC circuit. Okay. And this is a pulse. So we know about the impulse response of a series RC circuit. When a series RC circuit is excited with an impulse, the charge automatically rises up and then charge depletes. So that is what it is, right? Again, it is a flipped version, okay, time flipped version, okay? And this is an input. So we are now trying to figure out what would the response be if the input, instead of being an impulse, if the input is a square pulse. So of course, it's just like charging and discharging. So as long as the pulse is there, the capacitor will charge, and then the capacitor will discharge. Let's see that. So I am increasing the value. The overlapping area is increasing. Right? Overlapping product area is increasing. So this is the charging happening, right? Okay. This is where the maximum charge happens. At t equal to 4, the maximum charge happens, right? So when I am removing the input. Okay, so the input is high, so the capacitor is charging, and now beyond that the capacitor will discharge, and that can be seen through this convolution. The area is actually convolving area is reducing. So now this is denoting the discharge of the capacitor, discharging of the capacitor in a series RC circuit. Okay. This is again represented through convolution of these two signals. And again I shall give you these files. So don't worry about these. Okay, right. Let me show you a few more examples. Let me reset it back to 0. Say two trapezoidal pulses. Okay, so we have two trapezoidal pulses. Again, the red one is flipped. Okay, otherwise they would overlap with each other. Red one is flipped, and again I am calculating the overlapping area. See the how the overlapping area is denoted. Again I am integrating. And the output goes down to 0. Let's set it back to 0 again, and say two triangular pulses. Okay, the name is wrong. Okay, one triangular pulse, one rectangular pulse. Okay, so this is the impulse response of a system. Okay, and this is the input to the system. Okay, again this is the flipped version of the signal. Otherwise the signal would look somewhat like this. So we are again trying to find out the convolution of these two signals. See, so if I do the convolution, I can go back. Let's go back. Okay, let's go back. See it the other way around. Yeah. So again, this is the flipped version, right? This is ht minus tau. Keep that in mind. Okay, and that is how the convolution is working. So again, under these questions, you have to actually multiply those two signals and integrate, right? And finding the area might not be as easy as we actually did today. But in any case, that will be the end of discussion. Today's discussion. Feel free to ask any question you might have, because we are going to end our discussion today. But that's how convolution really works. Okay. So whenever a system is excited with an input, okay, the output can be considered to be a convolution of the impulse response of the system with that input. That is the entire idea. And for LTI systems, the impulse response of the system is identical, okay, to the system itself. So all the behavior of the system, entire behavior of the system is encapsulated within the impulse response of the system. So with that said, I would end today's discussion. I'll be here for 5 more minutes. If you have any question, please feel free to ask. Right, so this will be your homework for today. Thank you for all of you for patiently staying throughout the class. Say the impulse response of a system is given by this. You can always draw them, right? Because I taught you how to draw these things. And the system is excited with a signal that is represented with So question is, find the output of the system through convolution. So right. So that bit for today. Please, again, I'll be here for 2 more minutes. If you have any question, please feel free to ask. So thank you all of you for joining, and I shall let you know about the next class. In next class, we shall actually start Fourier transform. So please be there. Otherwise, you'll be entirely at a loss for the next 2 more classes. In any case, if you have any query, you can always email it to me. I'll be always there to answer your questions. So thank you very much for joining. So we shall leave our discussion today at this point. Okay. So if you have no more questions, I would end the discussion today. Thank you once again. Yeah, merci beaucoup and adios.